Ever wondered how doctors can spot tiny tumors or map organs in 3D scans? It's like solving a puzzle with thousands of pieces. Each slice of a CT or MRI scan is a clue, but putting them together accurately is a huge challenge. Traditional AI models. They're either too slow or miss the tiny details that matter. But here's the good news. A new model called MLRU++ is changing the game. Let's break down how it works and why it's a big deal for healthcare. So why is 3D medical imaging so tricky? Imagine trying to find a speck of dust in a stack of 1,000 photos. Each image is a 2D slice, but the real action happens in 3D. Traditional models like UNet struggle to balance speed and accuracy. They either take forever to process scans or blur the lines between structures like blood vessels and tumors. Then there are transformer-based models, which are great at seeing the big picture but act like a supercomputer for a smartphone task, way too slow and resource-heavy. Enter MLRU++, a smarter, faster way to tackle this. Think of it as a hybrid superhero. It combines the precision of convolutional networks, which spot local details, with a global vision of attention mechanisms. But how does it do it? Let's dive into its two key innovations. First up, the Lightweight Channel and Bottleneck Attention Module, LCBAM. This is like a spotlight that highlights the most important features without slowing things down. Traditional attention systems are heavy, like using a sledgehammer to crack a nut. LCBAM streamlines this by swapping complex math for simpler operations. Think 1x1 convolutions and depthwise layers. It's like replacing a multi-lane highway with a single-lane road that's way faster and uses less fuel. Here's the trick. LCBAM focuses on two things. First, channel attention. It identifies which features matter most, like the texture of a tumor, using lightweight 1x1 convolutions. Then, spatial attention. It zeroes in on where those features are located, using a 7x7 depthwise convolution instead of a full 7x7 filter. This cuts computational waste by 90% while keeping precision. It's like having a magnifying glass that only zooms in on the parts you need. Next, the Multiscale Bottleneck Architecture. This component tackles the challenge of capturing details at different scales. Think of it as a set of microscopes with varying magnifications. Traditional models either miss fine-grained details or get lost in the noise of larger structures. MLRU++ multiscale design uses hierarchical processing to analyze features at multiple resolutions simultaneously. By combining low-level textures with high-level context, it ensures nothing is overlooked, whether it's a 1 nodule or a 5 cm mass. So why does this matter? Medical imaging often requires massive computational power, which can be slow and energy-hungry. LCBAM changes the game by running efficiently on low-power devices. Imagine a handheld scanner or a smartphone doing the work of a hospital's mainframe. This opens doors for faster diagnoses, cheaper tech, and even AI tools in remote areas with limited resources. It's not just about speed, though. By reducing energy use, LCBAM helps make healthcare tech more sustainable. Think of it as a win-win for patients and the planet. Next time you hear about AI in medicine, remember, innovations like LCBAM are quietly powering the future of care. Thanks for watching. Hit subscribe for more deep dives into the science shaping our world.